تأكد. طيب it's recording. طيب now last class we have started with module 7. We talk about the MAC addresses, logical link control, physical link control, or the MAC address, sorry. We talk about the Ethernet frame fields. We discuss the purpose of each frame, and we talk about the transmission. Also MAC address, it's a hexadecimal, the length 84 bits, 48 bits. We talk about the organizationally unique identifier, which will be assigned by IEEE, and the vendor assigned MAC address. Once we combine them together, we have 48 bits MAC address unique bare Ethernet. Finally, we talk about the frame processing, how we can process the frame, what's the destination and the source MAC address should be in case we are using a unicast, transmission, broadcast, and multicast. Now we are going to talk about the same issue and continue our discussion. We need to talk about the MAC table, MAC address table. Now, a layer 2 switches or layer 2 Ethernet switch. When we say layer 2, we are talking about the data link layer. A switch operator, the data link layer, not the network layer. Uses layer 2 MAC address to make forwarding a decision. Now, according to the MAC address, the switch will make a decision. Where should I forward this data or this frame? It's completely unaware about the data protocol being carried on the data portion of the frame. Ethernet switch will not know any information about the protocol used in the upper layer. We are talking about the data portion, الجزء اللي خاص بالداتا بالفريم. For example, if it's IPv4, IPv6, if it's address resolution protocol message, ARP message, or if it's IPv6, neighbor discovery message. And we are going to explain what is this and this. في حد عنده مشكلة بالسكرين؟ بسرعة لو سمحتوا.
نو دكتور.
طيب تمام. الطالب اللي عنده مشكلة بسكرين يخرج ويرجع بسرعة. So, the switch will make its forwarding decision based only on layer 2 Ethernet MAC addresses. So the switch will examine the MAC address on the frame. Which MAC address, the source or the destination? The destination. According to the destination MAC address added to the frame, the switch will make a decision. Where should I forward this frame? So Ethernet switches will check its MAC address table. Every switch will maintain a MAC address. كل switch راح يكون عنده MAC address. What we have in this MAC address? The port and the MAC address of the connected devices, as you will see later on, to make a forward decision for each frame. Now, unlike the legacy Ethernet hubs that repeat the bits out to all ports except of the incoming port. So, what does that mean? It means that layer 2 switches will check the destination MAC address or examine the destination MAC address. According to that, it will make a decision to forward the message. Now, what's the difference between layer 2 switches and the hubs, the legacy Ethernet hubs? The hub simply will receive the frame from one port and will broadcast it, will send it out to all other ports except of the incoming port. So one input, many, all outputs. So it's a broadcast actually. So when the switch is turned on, the MAC address table is empty. For any switch, when we switch it on, we will have an empty MAC address table. So what we will do, the switch will learn, will maintain, will update the entry of the MAC address table. So MAC address table is sometimes called as a contained addressable memory, CAM table. So let us discuss it in more details. How the switch will learn this MAC address connected to which port by using the following operations. So we have a learning and we have forwarding operations. Two tasks. The first one, let us talk about the learning. Now, every frame that enters the switch is checked for information to learn. So what the switch will do when the switch receives any frame? It do this by checking the source MAC address, the sender of the frame, and the port number from where this frame comes to me as a switch, where the frame entered the switch. So the switch during the learning will check for any incoming frame, source MAC address, source, be careful. We are at the learning process, and what? The port number. Now, if the source MAC address does not exist where? At the switch MAC table, MAC address table. It will be added to the table along with the incoming port, which means what? The switch will add, for example, this one, port 1 received a message. The switch received a message from PCA with this MAC address at port 1. Now the switch will check its MAC address. This is the MAC address. Is it exist? No. This is the first time I'm receiving a frame from this port from this MAC. Good. I will add this MAC address to my table. This is the switch. So the switch will add the port number and the MAC address of that device connected to port number 1, which is a device number or a device A. Same situation. For example, if D send a frame to the switch will check the source. If it exists, we have a different access. This is the first time. It's not listed in my MAC address table. So I will add the port number 4. I will add the MAC address 00-0D. And so on. What we call this learning process. Now, so in case it's not exist, it will be added. Now, what if the source address do exist? What if I already have port 1 and MAC address and I have received a new frame? Simply, the switch will not do anything except of what? Refresh the time. Because every MAC address have a limited time to be added to the MAC table. If it's not used within 5 minutes, it will be removed from the MAC address table. So if the source MAC address does exist, the switch will update the refresh timer, which means reset. Okay, I have received a frame from BCA. Refresh the time for 5 minutes. If I did not receive any frame from BC1 at this port within 5 minutes, the MAC address details of that port will be deleted from the MAC address table. And we will back to the learning process one more time. So we are going to refresh the time. By default, most the Ethernet switches keep the entry in the MAC table for 5 minutes. So what's the default time for the MAC address table entry at any switch? Multiple choice question, 2, 3, 4, 5 minutes. The correct answer is 5 minutes. Now, what if this MAC address was on the MAC address table at port 1 and PC1 now BCA connected to port 2? So we have updated the port. So it exists, but from different source. Simply, it's like the learning. If the source MAC address exists, but on different port, in this case, the switch will treat this as a new entry. The switch will consider it as a new learning. So the entry will be replaced on the MAC address table, but on a new port number. So what will happen? For example, BCA now transfer a frame at port 2. We are going to consider this as a new entry. So port 2 with this MAC address. What's the time? 5 minutes as a default refresh time. What we call this learning process. Now, what about the forwarding? How the switch will make a decision? I have received this. I need to send it out to the destination MAC. Now, if the destination MAC address is unicast, which means one-to-one transmission, the switch will look, the switch will examine for a match between what? The destination MAC address of the frame and its MAC address table. So the switch will do a matching process between the destination MAC address on the message and the MAC address table. If the switch finds a match, it will be forwarded out to that specific port. Example, we have this. The destination is what? The destination MAC address of the BCD. Now the switch will examine the destination MAC address. Destination MAC address 00-0D. Is it on my MAC table? Yes. Which port 4? So the message will be switched to port 4 and it will be forwarded to BCD. In case the destination already exists on the MAC address table. Now, what if the destination is not in the table? What if there is no match? Simply, if the destination MAC address is not in the table, the switch will forward the frame out to all the ports, so it will become a broadcasting here, except of the incoming port. What we call this a process, a non-unicast. So in case BC4 is not here, so the switch received a message at port 1 from BCA. Now BC4 is not in the MAC table. After we do the matching, there is no match. What we will do, the switch will forward the frame to port 2, 3, and 4, except of the incoming port. What we call this? A non-unicast. Now, what if the destination MAC address is a broadcast? What if the destination MAC address is multicast, a multicast group? The frame will flood it out, will send it out to all the ports except of the incoming port. Simply, this is the action. I have a broadcast, all ports except of the incoming port. I have a multicast group, all ports. So only those on the group will accept it. Any other host does not belongs to that multicast group, as we have said before, will what? Will discard the message. واضح؟ So as the switch receives a frame on different devices, it's able to populate its MAC address table by examining the source MAC address for every frame. So the switch will continue learning from what? The source MAC address of all the incoming frames. When the MAC address table of the switch contains the destination MAC, it's able to filter the frame out to that single port only. It will become a unicast in case the destination it's already on the MAC address table of the switch, layer 2 switch. Now, you can refer to Net Academy and watch this video. It's explain exactly learning a process, forwarding a process. Now, last topic we are going to talk about the speed and the forwarding methods, how the frame will be forwarded on the switches, on Cisco switches. Now, Cisco switches use one of the following two forwarding methods in order to forward the data between the network ports. So the switches can use one of these two methods in order to send the frame from the N to the out port. We can use store and forward switching or cut-through switching. So what's the difference between them? If the switch operates by using store and forward switching, simply the frame forwarding method or the switch will receive the full frame, the entire frame, and will compute the CRC, cyclic redundancy check. Will calculate the CRC value. Now, if the CRC value is valid, the switch will look for the destination MAC address in order to determine the outgoing port or interface. After that, the frame will forward it to the correct port. So, store and forward, receive the frame, calculate the CRC, make sure it's a valid frame, then send it out to the destination port. What about cut-through switching? It's totally different. The frame forwarding method will forward the frame before it is entirely received. Before we receive the full frame, it will be forwarded to the outgoing port. At least once we receive the first 64 bytes, the forwarding decision will be made. So at a minimum, the destination address of the frame must be read. So at least once the switch read the destination MAC address, before reading the other parts of the frame, the switch will make the forward decision. So first one, receive CRC, valid, forward. Second one, cut through. The switch will read the MAC address, destination MAC. What's the destination MAC address? Read it. The switch will make the forward decision, even if not the entire frame is received. So, the big advantages now of store and forward switching that it determines if the frame has an error before propagating the frame, before sending the frame or not. When an error is detecting in the frame, the switch will discard the frame. This is the main disadvantage, of the store and forward. We are going to test, check. If it's valid, it will be forward. If it's not valid, it will be discarded by the switch. So what's the benefit here? We are going to reduce the overhead. We are going to improve the bandwidth. So discarding a frame with errors will reduce the amount of bandwidth consumed by the corrupted data. So it's a big advantage to improve the performance. But receive the frame, calculate CRC, check the validity, then send. High latency. We have a latency here. Delay. What about store and forward? Store and forward switching is required for the quality of service. A streaming, for example, a VoIP. VoIP frame will have what? A high priority to be forwarded immediately. We need to have a low delay in this case. So it's a good transmission method selected for this type of traffic, voice traffic, for example, because its priority will be higher than the browsing traffic, so it will be transmitted immediately. Now, we have two sub-methods in cut-through switching. In cut-through switching, the switch acts upon the data as soon as it's received, even if the transmission is not complete. So the switch buffer is just enough of the frame to read the destination MAC address, so it can determine to which port it should be forwarded out. The switch does not perform any error checking on the frame. So, cut-through switching, immediately the decision will be made after we reading the destination MAC address. No error checking is implemented on this method. But we have two different cut-through switching methods. We have fast forward switching, and we have fragment-free switching. Under cut-through switching. So it's sub-methods, let me say, or sub-techniques, comes from the main one, cut-through, not fast, not store and forward. So what's the fast forward switching? Now, fast forward switching will offer low latency, low delay, by immediately forwarding the packets after we read the destination address. So because fast forward switching starts the forwarding before the entire packets has been received, there may be at times when packets are relayed with errors. Some packets will be transmitted and those packets already corrupted. It has an error. So the destination network interface card will discard all the faulty packets upon receipts. So fast forward switching is typically a cut-through method of switching. It's typically considered what the cut-through switching methods. Fast forward after we read the destination address, will not check the errors. Some packets are already, including the error, will be transmitted to the destination device. What will do the destination? Once it's received, it will be discarded by the receiver. Now we need intermediate solution. We need to have a solution to this. We have a fragment-free switching. So simply fragment for free switching can consider as intermediate solution. It's compromise in the middle between the high latency and high integrity of store and forward switching. Store and forward actually provide high latency, delay. High integrity, why? Why integrity? Integrity means the frames will not be transmitted unless we have a valid CRC. So will not send a corrupted frame in this case. So it comes in the middle between store and forward switching and the low latency and the reduced integrity of fast forward switching or cut-through switching. So what the switch will do here? The switch stores and performs error check for only the first 64 bytes of the frame. On a fragment-free switching, the switch will store and check the errors on the first 64 bytes only of the frame before make the forwarding decision. Why? Because most of the errors and the collision occurs on the first or during first 64 bytes. So this will ensure that the collision has not occurred before forwarding the frame. So it's in the middle between fast forward switching and cut-through. How? And store and forward, sorry. How? Only store the first 64 bytes, check the error and the collision on the first 64 bytes, then make the forward decision. So we have a compromise intermediate solution to handle the high latency and the high integrity of the store and forward, or low latency and low integrity of the fast forward switching. واضحة؟ طيب, now finally, what about the memory buffering on the switches? Also, we have a buffering and we have a methods for the buffering on the switching. What's the buffering? Temporary storing the data, the incoming data. So Ethernet switch may use a buffering techniques to store the frame before forward them, or when the destination port is busy because of the congestions. اللي هو زحمة خلينا نقول على البورت. So in general, memory buffering switching can be divided into two main methods: port-based memory, shared memory. So for the port-based memory, simply frames are stored in a queue that are linked to specific incoming and outgoing port, a queue between the in port and the out port. The frame will be transmitted to outgoing port only when all the frames ahead before that frame in the queue have been successfully transmitted. So first in, first out. This is how the queue operates, FIFO, first in, first out. It's possible for a single frame to delay the transmission of all frames in the memory because of the busy destination port. Sometimes one port will wait for the queue because the destination port is busy. So all the frames after that one will wait until the transmission of this current frame is done. It's a queuing, in, out. They will enter from one side, exit from the other side. The inside is the in port, outside is the destination port. This delay occurs even if the other frames could be transmitted to open destination ports. So this is the port-based memory. Now, what about the shared memory? Shared memory simply will store all the frames in a common memory buffer shared by all the ports. A one common memory shared by all switch ports. And the amount of buffer memory required for each port will be dynamically allocated. Each port will allocate a different buffer size or memory size. So the frames in the buffer are dynamically linked to the destination port, enable packets to be received on one port and then transmitted to another one. We will not create a link between the in and the out port. We will receive the frame from one port to the buffer, then from the buffer to the outgoing port, without moving it to different queues. So no queues used here. Shared memory buffering will result in larger frames that can be transmitted with a fewer dropped frames. This is very important with asymmetric switching, asymmetric different data rate allowed or provided for each port. Asymmetric, مختلف. So with asymmetric switching, which allows for a different data on different ports, which means more bandwidth can be dedicated to a specific port like the server port, while lower bandwidth or less bandwidth can be dedicated to, let me say, less more important ports. A quick revision now about the duplex. We have talking about that the communication can have either a full duplex or half duplex. So two of the most basic settings on the switch are the bandwidth, the speed of the transmission, and the duplex setting on each individual port. It's critical that the duplex and the bandwidth setting match between the switch ports and the connected device, which means we have a connection between two ports. They should operate either full duplex or half duplex. One of them full duplex and the other one is half duplex, we have a problem. So we have two types of the duplex setting, as we have discussed last week. Full duplex means both ends can connect, can send and receive at the same time, simultaneously. Half duplex, only one of the ends can send at the time. So how the ports will select the duplex and the speed setting through a process called auto negotiation. So they will negotiate. Port 1 will say, I'm using a full duplex. Port 2, I will use a full duplex too. So they agreed to use the full duplex. The transmission can start it now. What we call this auto negotiation. So auto negotiation is an optional function found in most of the Ethernet switches and in ICs. It's enabled two devices to automatically negotiate the best speed and the duplex. Keep in your mind, gigabit Ethernet ports only operate in full duplex. If it's a gigabit Ethernet, not fast Ethernet, it will operate only in a full duplex communication, not half duplex. Now, duplex mismatch, this is what we have talked about, is one of the most common causes of performance issue on 10 or 100 megabit per second Ethernet links. ما عندي أنا ما طلع لي أي طالب أسوي له acceptance أساس يدخل. ما طلع لي الطلاب ينتظروا. احنا ودينا لكم same link مسج اليوم. So, what we have here, we have a problem. It occurs, this one, the mismatch of the duplex mismatch. It occurs when one port on the link operates at a half duplex, while the other port operates at the full duplex. So switch one, a full duplex, I'm a full duplex, so I can send whenever I want. I'm a half duplex, so I can only send when the connection is clear. But I'm receiving a lot of collision because what switch one keep it transmitting. Keep it transmitting. So when the duplex mismatch is occurred, when one port, it occurs when one or both ports on the link are reset. We are resetting the link. So the auto negotiation process does not result in both link partners having the same configuration. So the port was reset without a new auto negotiation. What's the auto negotiation? S1, I'm going to use a full duplex. S2, I will use full duplex. So we have a full duplex connection. It also can happen when the user configure one side and forget to configure the other one manually. So the user configure S1 as a full duplex and forget to configure the other side, for example. So both sides should have auto negotiation on, or both sides should have auto negotiation off. So the best practice is to configure the both Ethernet switch port as a full duplex. And we already said that only the legacy Ethernet and the hubs operate on the half duplex by default. Let me say current Ethernet switching supporting the full duplex connection. Finally, we need to talk about the automatic medium dependent interface. Now we have talked about the cabling, and we have mentioned that we have two connection types, crossover or straight cabling. So connection between devices, once required that the use of either a crossover or a straight through cables. So the type of the cable required depends on the type of the interconnected device. It depends of the end or the connected device. We are going to select either a crossover or a straight cable. For example, in case we have a connection between a router and a host, what's the cable type will be? For sure, the cable will be, in this case, a crossover connection. So, how we can avoid this problem, selecting incorrect ending cable? Simply, most of the switches devices now supports what we call auto MDIX, which is automatic medium dependent interface. crossover feature. When this feature is enabled, the switch will automatically detect the type of the cable attached to the board and configure the interface according to the type. So it's automatically interface configured. So the Auto MDIX feature is enabled by default on the switching running the iOS release 12.2 series or later. However, the feature could be disabled as well. So for this reason, you should always use the correct cable type. So do not rely on the Auto MDIX feature. Sometimes we'll select incorrect cable, MDIX is disabled. So we have a connection problem here. So how Auto MDIX can be enabled? By using MDIX Auto commands on the configuration for the interface configuration command. So we access the interface, then we simply type this command. We have done with, as I told you, it's less than an hour, the remaining part of session 7. Any question?